All right, welcome to another JNCIE-SP video. I'm hoping this can be a short one while my lunch cools off. So, don't like to eat food when it's too hot. So last video, we noticed an error with the commit. So this video, we're going to be troubleshooting and resolving that error. I think I already figured it out. So edit group, external peers, and if I do a show pipe display set relative, you can see, oops, I'm missing a command, and that command is going to be peer AS. So I'll go ahead and just show what that error message was before I fix it. So error in neighbor, group of external peers, AS number must be configured for an external peer. So there's no parents AS, there's only one peer AS configured for a specific neighbor, but as such, these kind of, since we've got type internal, so if I were to do edit protocols, oops, space key isn't working at all. Oh, yeah, that's interesting. The space key doesn't work. So edit protocols, BGP. Huh, okay. Well, Juniper's kind of sometimes a little bit strict about what you can and can't enter. But of course, you can always just start from scratch by using that Control U. But you can see, that's interesting too. I'm missing type external, it looks like. So, but that's no big deal to add. Edit group external peers. So set type external, set peer AS22. And hopefully that's all it needs. Perfect, yep, so that is just fine. Let's do a show interfaces terse. So all the interfaces look like they're up. They've all got their IPv6 addresses. On logical system A, configure the interface encapsulation, per unit number, and DLC to reach logical system E. We're not using logical systems. It's just kind of an extra layer of complexity that I don't think is going to be on the exam. So I'm just going to skip it. And we'll run another verification command. This looks like it's meant to be on E. Well, this is verifying the logical system again, which we're not doing. So let's just go straight down to the verification steps. This is just more information about how to configure it. Here's the final results. All right, so we'll start by verifying that BGP is running on configured interfaces and that the BGP session is active for each neighbor address. So on router E, we're going to do show BGP neighbor. And we're going to see 4 neighborships, 1, 2, 3, 4. And we can make that easier to see. Sometimes it's difficult to see the output sometimes. So gotta really get used to using that pipe match just to make things easier. 1, 2, 3, 4. Yep. So we got 4 peers. And of course, show BGP summary is probably your best command for just seeing if all your connections are established or not. And we can see, oh, there's going to be some issues we're going to need to troubleshoot. But that might be a topic for the next video because I want this one to be pretty quick. Maybe 10 minutes max. But let's take a look at the group, show BGP group. We got total peers 4, established 0. So that's another easier way you can see if all of your connections are not. Let's see if we can figure out why these aren't being established. So show BGP summary. pipe refresh 1. And let's start by troubleshooting the connection to router A and get the Wireshark capture going. Although there was that issue in the last video. So let's restart this and hopefully that will be enough to resolve that issue. Oh, looks like I've got it enabled on 2 of them. All right, thankfully that was all that was necessary. All right, so let's troubleshoot that connection and hopefully get it to go into established. Hopefully that rollback error didn't happen. Nope, looks like everything still configured for IPv6. It looks like well, actually it looks like it might have happened because the newest commit was, nope, okay, it's on there, so everything's good. Let's do a show BGP summary, pipe refresh 1. Maybe just take a look at the traffic because we're going to be getting traffic. Yeah, so here's a neighbor solicitation message. This is kind of like ARP for IPv6. It is what has replaced ARP. So you can see destination is, it's not going to be a broadcast address like all Fs or something like that. I believe it is unicast. It could be multicast. Well, let's take this as an opportunity to more about IPv6 neighbor solicitation. And maybe just kind of keep it simple and just figure out whether or not that's multicast or unicast. So neighbor solicitation. Hosts inquire with neighbor solicitation messages to locate routers on an attached link. Routers which forward packets not addressed to them generate router advertisements immediately upon receipt of this message rather than at their next scheduled time. So, oh, that's a router solicitation. This is actually, so it looks like we've got router solicitations, router advertisements, neighbor solicitations, neighbor advertisements, and redirects. So this is actually going to be a neighbor solicitation, not a router solicitation. So let's see what neighbor solicitations are. Neighbor solicitations are used by nodes to determine the link layer address of a neighbor, or to verify that a neighbor is still reachable via a cached link layer address. So I think it's pretty clear, since it's intended for a specific neighbor, that it is going to be a unicast address. One thing we can also do is do IPv6 neighbor solicitation unicast and see if somebody says, so typical neighbor solicitation messages are multicast for address resolution and unicast when the reachability of a neighboring node being verified. Okay, so that's kind of a, so here's from an RFC, which is a really good authoritative source. So here's the message format. And the destination address is either the solicited node multicast address or the corresponding to the target address or the target address. So it can be either multicast or unicast depending on certain factors. Okay, so let's figure out why it's not working. And I have a feeling it might be because of the extra knob that we added to A because we thought it was going to be part of a logical system and it was going to be going over frame relay. So I think the first thing I'm going to try to do is remove this knob, which is extended unique identifier, so EUI-64. And we're actually going to see if I do show ARP, or actually no, if I do a show int terse type match GE dash. Well, I think there will be a way. Let's just do show int. So there'll be a way to get, here we go, perfect. So here's the local address. So does this look familiar from the last video? Anyone recognize that? So let's try not to see the MAC address, try to keep that hidden. So I'm just going to copy this, it ends in a 2, and then open up a notepad. And then I'm going to cover up the whole screen so that nothing is ruined, and then it ends in a 2. And let's try to figure out what the MAC address of this interface is going to be. So we know that this is going to be something that separates the MAC address. So if you wanted to build this address, you would have a MAC address, which is 48 bits. In hexadecimal, it would be 2 sets of 6 octets like this. So in your first set of 6 octets would be here, this 1 EA 635, and then your second set is going to be F6 4A 02. Actually, it's going to be different because in IPv6, anytime you have a leading 0, you can get rid of that leading 0. So this is actually an abbreviation. The whole address is actually going to have a 0 here, and then it's going to have 2 more zeros, 3 more zeros here, and then this would have 4 zeros. If you have a block of all zeros, you can drop the block and just have a double colon. And then you can do that for any number of consecutive blocks of zeros. So if this were a 0, I could drop all of these and just write it like this. You can only do that for one consecutive or single block of all zeros, though, because otherwise it would get ambiguous if you had more than one colon. You couldn't tell because you can only have a total number of 128 bits. But if you use double colons, you couldn't tell which block of which set of 4 zeros contained only one set of 4 zeros and which one contained 2. You wouldn't be able to have any way of telling whether you're abbreviating a sequence of 4 zeros or just one instance of 4 zeros if you had multiple colons. So you can only use that abbreviation one time. You can only have one double colon to specify that you're abbreviating the zeros, but you can just drop all of the leading zeros. So if you have another block, you can just do :0, and that's plenty of abbreviation. All right, so let's go ahead and write out the full address without any abbreviations that we can see here. So we've got 128 bits. Each of these is 8 bits, and each individual character is 4 bits. So now from here, it's going to make a lot more sense. We can see here's the extra part that was interjected into the middle of the MAC address. So now we've got the 6-bit, the 6 nibbles, or the 3 octets in the second half of the MAC address. And then we've got the same thing here in the first half of the MAC address. So I'll move that down to a second line. Then I'll go ahead and, so that's our kind of step 1, and we're reversing it. So now our step 2 in our reversal is to take this out. So I'll just leave that out. And then our step 3 in our reversal process, we're going to be putting it together now that that is out. And then the final step, we got to flip the 7th bit from the left from a 1 back to a 0. So we know that these all represent octets. So first half of that first octet is going to be all zeros. And then the second half is going to be E. So we know that F is the highest, and that's going to be 16. And we know that E is 1 less than F, so that's going to be representing a value of 15. So really easy way to do that. We know all bits on is 16. We know the last bit is 1, so we want 16 minus 1. So that's what we got for our binary representation of the hexadecimal digit E. But we need to flip the 7th bit. So let's go ahead and do that. And that's going to decrease it by 2. So A, B, C, D, E. So now we've got a C instead of an E. So our MAC address is going to be 0C A635F6 4A02. So let's verify that the MAC address of interface GE000 is going to be this. And the way we figured that out is simply by reverse engineering the EUI extended unique identifier that was assigned as the local IPv6 address on this interface. So in order to get that MAC address, we're going to need to, let's see here, look at detail. Well, we're going to need to, whatever command we need, we're going to need to figure it out because I don't know off the top of my head. Extensive. Okay, well, it's going to be more difficult than I thought to find that MAC address. So show interfaces, we've got media, we've got extensive, we've got brief. Sometimes, I don't think it's very often, but sometimes brief actually gives you more information than extensive because it includes a field that wasn't included in extensive. I think that's pretty rare. SMP index. Oh, that worked. So I did show interfaces, GE001 SNMP index, and then just kind of out of curiosity or desperation, whatever you want to call it, I just included the number 1, and here's the current address. So let's see if that matches what we reverse engineered. So the first part looks like it definitely matches, but the second part looks like that does not match at all. So maybe this, because I just kind of picked this at random, maybe this isn't actually for the physical interface itself. Maybe it's for something else, but kind of good news knowing that the first part was right anyway. We got that bit flipping correct. So yeah, not sure what command would be the best for figuring out MAC addresses, but this is kind of another running theme behind this channel. If you don't know, it's just one Google away. So Juniper interface MAC address. Show interfaces MAC database. Let's try that. Oh, and we got to specify a specific interface. So let's specify that 0. So that's command's not going to do it. Here we go, MAC address. Oh, let's see here. Show interface doesn't tell you the MAC address of the interface. So let's see what help this person has got. Let's go to the solution. So, oh, apparently it does. You just can't read. So we're going to see QoS queues. Or we're going to see from top to bottom, interface index, link type. Yeah, I don't see where this aligns. This clearly isn't the same output that they're saying here. Yeah, I don't see hardware address isn't even pipe match hardware. Yeah, there's nothing like that in the command. So I'm looking at the logical unit. Okay, so you do get it when you look at the physical interface, just not with the logical unit. But it's going to be the physical interface, even though the IPv6 address is assigned to the logical unit. EUI, extended unique identifier, 64, that's going to be using the MAC address on the physical port. So now we can verify. Let's redo that command, but let's do a pipe match. We got it. So we were able to successfully reverse engineer and figure out what the MAC address is on that port based on how we know a local address is assigned from IPv6 using the EUI extended unique identifier protocol or method. All right, so let's continue. Let's verify the. Oh, actually, well, we've got to figure out why these aren't coming up. Okay, so I'm going to try removing that knob. Oh, can't assign. Oh, yeah, that's interesting. Why is it saying to assign a network address to a interface? Is that something that the documentation says to do? Oh, it does. So maybe it's specific to, maybe it's only possible because it's a Delta interface. So I might need to actually assign host addresses instead of network addresses just because I'm not using frame relay. Like you might be able to do that special because you're using frame relay. Okay, so yeah, I guess I'm willing to say that that's the problem here is just because I'm not using the special setup. that they have in this lab. I'm going to not be able to use this knob for one, and I'm going to have to use a host name. So stay tuned for the next video where I make those configuration changes, and hopefully that resolves the problem. So thanks for watching.